All right, welcome back to another installment on my series of videos on working with a representation called arrow diagrams. We're going to use our arrow diagrams this time to solve this equation. This touches on a number of different ideas, and we'll just kind of plow through this example right now, and then we'll have some of the discussion at the end. Okay. So, as always with the arrow diagrams, I'm going to start with the independent variable. Here is my x. And the first thing that happens to that x, it gets multiplied by a 2. Done this differently in different places. At this point, for this, the intermediate writing that down is, well, I'm going to go ahead and do it. It's not necessary for this, but I'm going to do it anyway. Okay. My next step then, to change the 2x, it needs a negative sign in front of it, so I'm going to do a sign change there and get my negative 2x. If you've been watching these, you recognize this process. So now I'm going to add 5 onto that because of the commutative property of addition that can be written as 5 minus 2x so that it matches what I have in there. This now, 5 minus 2x needs to end up in the denominator though, so I'm going to flip it. I flip it with the reciprocal function, and so this gives me a 1 over, 5 minus 2x, but it's supposed to be 3 over 5 minus 2x, so I'm back to blue here, and so if I multiply by 3, I will get that 3 over 5 minus 2x. Okay. So I've verified everything along the way there. I am now, kind of as a point of emphasis, I'm going to erase these things at the end of the arrows. When I get good at these, there's only a few instances where I actually need that stuff in the middle. But this is the clean arrow diagram for this expression on the left-hand side of the equation. Now, solving the equation means I want to know what value of x I can put into the left side of the equation so that I get a 4 out on the right side of the equation. Okay. So, my farthest right output here, my output says I'm trying to get a 4 right here. Okay. Well, I need to get that 4 from the right-hand side all the way back over to the left-hand side where the x is. And so what I need is paths that go back the other direction. Okay? This is the concept of the inverse of this. So if moving this direction was multiplying by 1/3, by 3, then the inverse of that is multiplying by 1/3. Those are multiplicative inverses of each other. And if I started with some number at the beginning of this solid blue arrow, and I multiplied by 3, and then I followed the dotted blue arrow back and divided by 3, I would end up as basically a closed loop that undoes everything that, that the one arrow did to it. So we end up cycling right back to an identity, which is the test of an inverse. Okay. All right, we're also going to need the inverse of this. The inverse of the reciprocal function is, interestingly, the reciprocal function. If you flip something over, the way to get it back the way it was is flip it back over again. Okay. That's one that we can experiment with in another time. If you're not convinced of that, pick a number, put it at the beginning of the solid black arrow, flip it over, get to the other end, follow the dotted arrow back, and flip over again and see if you don't get back to the number that you started with. Okay? It's an easy one. Our additive identity is 0, so our additive inverse is -5. So if we add a -5 or subtract 5 there. The inverse operation of a sign change, if I change the sign on something, then I'm going to change the sign back. And then finally, on this, with the multiplication by 2 here, this is going to be a multiplication by 1/2. And so if I watch and I follow what happens to this 4, I'm going to move it down so it's out of the way here a little bit. It says the first thing that I should do to this 4 is divide it by 3, or multiply by 1/3. That will change it into a 4/3. Okay. The 4/3 is now at the end of the dotted blue line, which means it is at the beginning of the dotted black line. I want to use that one because it's getting me back in the direction that I want to go, closer to the x. And so if I flip a 4/3 over, I get a 3/4. And then that's at the end of the dotted black. It's at the beginning of the dotted green. So I'm going to bring the dotted green arrow, follow that back here, and subtract 5, which is 20/4. So that'll leave me at negative 17/4. At the end of the dotted green arrow, that's at the beginning of the dotted red arrow. So following the dotted red arrow, this direction, it says change the sign on that, so that just becomes a 17/4. 17/4 is at the end of the dotted red arrow. It's at the beginning of the dotted blue arrow, so if I follow that, and half of 17/4 becomes 17/8, which is where the x is. So my solution to this equation is x equals 17/8. Okay. Can I check that? I'm always supposed to check these kinds of things. Well, the way to check it is to start the 17/8 at the beginning and evaluate 17/8 on the left-hand side here. And I can see when I multiply it by 2, I'm going to get 34/8, which reduces to 17/4, like I have down here in red. I'm not sure if I can kind of indicate where I'm looking there. And then if I change the sign on that, I get to this negative 17/4. When I add 5 onto that common denominator, that's a 20/4 is 5. And 20/4 minus 17/4 gives me the 3/4. I flip that over, it's a 4/3. I multiply by 3, and it spits 4 out the end. So as long as I know what these dotted arrows are for each of the arrows that I made across the top, the solid arrows, then I should be able to do this and solve equations. That doesn't work every single time, but because not all solid arrows that you might create will have an inverse arrow that goes with them. But if you spend some time looking at this, there are some very interesting implications here in terms of the inverse of 3/5 minus 2x. I think in some sense that is staring us in the face there. Some implications with regard to transformations of functions, composition and decomposition of functions, proving two functions are inverses of each other. It's a lot of things like that that you may be able to see in this if you look carefully at it.